No, not launching. No, but we were having.
Okay, we're going to start. So this morning we've got a session on planetary magnetism. And so our first speaker is Jerry Bloxham.
Well, good morning. It's a great pleasure to be here, and I particularly like to thank the organizers, in particular Emmanuel, who put up with not only COVID, but people like me who kept changing their mind as to whether they could come or not. So thank you. The work I would like to talk about this morning is much more distinctly observational from what we were hearing yesterday. And it's not just my work, it's the work of my colleagues at Harvard, or formerly at Harvard, since in the last few months, 3 out of 4 of them have left. And also the other people on the Juno science team, which is an indication that some of what I will be talking about today is in connection with the Juno mission to Jupiter. So an outline of what I'm going to talk about. In the first part, I will follow my orders from Emmanuel to give an overview of planetary magnetic fields. And I thought I'd take a slightly contrarian viewpoint and argue that actually there are far more differences between the planetary fields than there are similarities. And then I'll go on to talk about some of the issues that arise in analyzing planetary magnetic field data, and then at the end take a somewhat closer look at Jupiter and some of the new data from that planet. So I'm starting off with an old slide that I dug out from a talk that I gave maybe 20 or so years ago, showing just the dipole components of the then 5 planets that we believe to have active dynamos. We didn't know much about Mercury back then. And based on that slide, I think we felt that the planets basically fell into 2 groups. One with near axial dipoles centered near the planetary center, and 2 with very non-axial dipoles displaced far from the planetary center. And one of the things that got me excited about a mission to Jupiter was I felt that Jupiter was perhaps an analog for the Earth, that it's got a similar dipole tilt. Its magnetic field back then we thought of as looking fairly Earth-like, but for observations, Jupiter has a big advantage that we can get much closer to the dynamo region with a spacecraft than we can for Earth, and there's no awkward crustal fields polluting the signal coming from the dynamos. So in some ways, Jupiter seemed like a better planet to study if we wanted to understand Earth-like dynamo action. Observations tend to sort of change that somewhat naive thinking. And here is where we stand today. Mercury's magnetic field, not particularly well sampled in the southern hemisphere, but is axisymmetric to a large extent, but displaced northward along the rotation axis. So the field is much stronger in the northern hemisphere than it is in the southern hemisphere. This came to light from the observations from MESSENGER. Earth has a magnetic field which we can only see up to about spherical harmonic degree 13 because of the crustal field. But I would characterize it as a very spotty field. We got spots of flux, concentrations of flux, more or less sort of filling the whole of the core mantle boundary region. This is a surface map. This one is downwardly continued to the core mantle boundary. Jupiter, here downward continued to about 90% of the planetary radius, where we believe the electrical conductivity is becoming larger. It's characterized by large regions in which the flux is actually very weak. We don't see that for the Earth. The Earth is fairly full on over the whole surface of the core mantle boundary. Jupiter, on the other hand, we got large regions of very low flux, punctuated by this one concentration of flux on the equator, which we unfortunately jokingly referred to as the great blue spot, and that terminology seems to have stuck, and a band of flux in the northern hemisphere, which is strong. Elsewhere, the field is relatively weak, but quite dipolar. Saturn has a field which, and this is from Cassini observations, where the more closely or the more refined the observations get, the more we find that the dipole tilt is small. It's just getting smaller and smaller in the bound we can put on it as the observations get better. Slightly displaced along the rotation axis, but to all intents and purposes, a very axisymmetric, nearly centered dipolar field. Then Uranus and Neptune, perhaps somewhat alike, only alike in that they're so different from the other planets, with dipoles forming a very poor representation of the field. Neptune in particular also has large regions of fairly weak field like Jupiter. So these 6 planets are really all somewhat different in the magnetic fields that they have. One thing I would love to see is another mission to Uranus. I think that's the most interesting planet to study at the moment. The NASA Decadal Survey in Planetary Science recently ranked that as the top priority. That doesn't mean it's going to happen. And even if it did happen, we wouldn't get data for about another 25 years from now. So that's not something to sort of be holding our breath waiting for. So how can we go about explaining some of these differences between the planets? Well, the planets no doubt differ in structure. Those with a magnetic field undoubtedly have a convecting, electrically conducting region in their interior. And unfortunately, for all the planets, that convective region where the magnetic field is generated is masked by either a mantle or an atmosphere. We don't see the convective region directly, either in the case of the Earth, a solid mantle gets in the way, or in the case of, say, Jupiter and Saturn, a dense hydrogen atmosphere gets in the way. So we can't see directly what's happening. We might add some complexity to that model by adding a solid non-convective region in the center. And we might add further complexity by adding a stably stratified region at the top of the convective region, or a stably stratified region at the bottom of the convective region. These are all complications which we can imagine adding to our simple sphere of conducting fluid, which Andy talked about yesterday. In addition, the electrical conductivity structure varies for these planets. For Earth and Mercury, it's more or less discontinuous at the bottom of the mantle. You go from low conductivity to high conductivity abruptly at the base of the mantle, whilst for Jupiter and Saturn, and most likely also for Uranus and Neptune, the electrical conductivity increases through some region in which the transition, in the case of Jupiter and Saturn, to metallic hydrogen, in the case of Uranus and Neptune to conducting ionic ices, is taking place. So the bottom line from this is we're not short of opportunities to build interior models that may give dynamos that have particular properties. Actually, let me go back. On the right here, I've listed in sort of some rough order of decreasing likelihood which of these features each particular planet has. One could certainly argue about whether it's more likely in planet A than planet B, but obviously, as I said, all have a mantle or atmosphere that gets in the way of seeing what's happening in the conducting region. All necessarily have a convective region if they're generating magnetic fields through dynamo action. A solid non-convective region, certainly for the Earth, likely for Mercury, fairly likely for Saturn, reasonably likely for Jupiter, although none of these things we can be absolutely certain about. A stably stratified layer at the top, most likely for Saturn, as helium rains out of metallic hydrogen. Possibly for Jupiter, although one may go through that transition in Jupiter rather quickly, as the pressure and temperature in Jupiter increases much more rapidly than it does in Saturn. Or if your blob of helium dissolved in hydrogen, you see it decreasing more rapidly as you go upwards. A stably stratified region at the bottom, Saturn and Jupiter, from possible dissolution of the solid inner core into the overlying hydrogen. The hydrogen's really hot, so most things will dissolve in it. And the inner core, Earth and Mercury, Saturn and Jupiter, as I mentioned. Okay, so there's two approaches that can be taken to trying to explain this wide variety of planetary magnetic fields. One is to say that, well, we can add increasing complexity to the dynamo models, given this sort of large number of degrees of freedom we've got to play around with building a planet, and to see how that affects the magnetic field that is generated. And Sabina Stanley's work and Uli Christian's work with his colleagues has shown that one can produce a range of different magnetic field morphologies by changing the structural properties of the model. On the other hand, one could look at structurally more simple models and find a range of different solutions as the control parameters are varied. And Chris Jones's work back in 2014 showed how a sort of Jupiter-like simple model could produce quadrupolar fields, hemispheric fields, dipolar fields, just by looking at different parts of parameter space. And an example of this is trying to explain the very small dipole tilts that have been observed by Cassini for Saturn. In a recent paper, Yan and Stanley, using a structurally complex model with stably stratified layer at the top with lateral heat flux variations above that layer, obtained dipole tilts as small as 0.06 degrees. But on the other hand, in other work, Rakesh Yadav has found with a simple model without complexity of stably stratified layers, dipole tilts as low as 0.0008 degrees in a dynamo model. This undoubtedly only exists in a small region of parameter space, but it's important as an existence demonstration that you can find dynamos with extremely small dipole tilt with simple structural models. So that raises a question, which is more important? Is it the structural difference between the planets, or is it the fact that they're happening to operate in different regions of parameter space? Now, undoubtedly, that's not an either-or question. It's some of each. But it does mean we've got to be careful if we try to induce interior structure from the magnetic field morphology, because we know, at least in the case this demonstration for Saturn, that we can produce complicated, or actually extremely simple, very low dipole tilt with a very simple model without having to appeal to extra complexity. So I think this is an issue which needs to be thought about carefully, that we can't simply say these two planets have very different magnetic fields, therefore there's something very different about their interior structure. I wish we could say that, because I'd love magnetic fields to be a really sensitive probe of interior structure of these planets, but I'm not quite sure that's necessarily the case. Okay, so what I want to move on to is to talk about some issues that arise in analyzing these planetary magnetic fields, and in particular to draw a distinction between the Earth and the giant planets. For the Earth, analyzing magnetic fields, I will argue, is relatively simple, but there are some important complications that arise when we look at the giant planets. And I think the discipline has been a little bit guilty of trying to pretend those complications don't exist, but they obviously do. So for Earth, we have a situation where we've got a mantle, which is essentially electrically insulating. We have an impenetrable, spherical, very nearly spherical core mantle boundary, and we've got a highly conducting convective outer core. So the electrical conductivity is near zero until one reaches the core mantle boundary. Then it jumps discontinuously to a high value in the liquid iron outer core. So that means we have no problem, well, we have some problems, but we have relatively few problems in taking observations made up here and downwardly continuing the resultant models to this boundary on which the electrical conductivity jumps discontinuously. But the magnetic field, or its radial component, is continuous across that boundary and across the thin boundary layer at the top of the core, so that surface observations tell us what the magnetic field is at the top of the free stream in the outer core. For Jupiter and Saturn, the picture is more complicated, because even though we have an initially electrically insulating region atop the highly conducting convective region, and the grayscale gradation here is a little misleading, over a fairly small radius range, the electrical conductivity goes from very low values to quite high values, probably higher than in the Earth's core. And so there's no one point at which we can say, okay, we can downward continue to this radius, at which point the electrical conductivity is high. Instead, we're downwardly continuing into a region in which the field is becoming increasingly non-potential. But we need to get down to depths at which the electrical conductivity is reasonably high, so we can use some of the ideas that we have used in the past about frozen flux to infer something about what's happening at the top of the convective region. There's no simple radius at which we can say downward continue to here, and then apply frozen flux. It just doesn't work that way. And of course, these pictures aren't to scale. So in the Earth and the giant planets, we know that in the conducting region, the magnetic Reynolds number is very large. But in Jupiter, maybe 10 to the 5. We're looking at large magnetic Reynolds numbers. So in both Earth and in the giant planets, flux is frozen in the sense of Alfvén's frozen flux theory. But that's different from saying we can then apply the Robertson-Scott-Backus theory of the secular variation in highly conducting cores. This is undoubtedly the case. This is depends upon an additional series of assumptions. So what else is needed in order to apply Robertson-Scott? Well, we need to be able to downwardly continue near surface observations to the region of high magnetic Reynolds number. As I said, for the Earth, that we can do. For the giant planets, it's less certain that we can do that. We need an impenetrable radial boundary. The Robertson-Scott theory is based on the radial component of the flow vanishing, which simplifies the radial component of the magnetic induction equation. That we have for the Earth. We don't have that for the giant planets. Incompressible flow, again, simplifies matters. We have that for the Earth. We don't have that necessarily for the giant planets. So we can't simply choose some radius, 0.9 of the planetary radius, say we'll downwardly continue to that depth, and all will be well, and we can apply Robertson-Scott in the giant planets. It just doesn't work that simply. So is there any way we can look at how this actually works in practice? Well, what I want to show here is some insights we might gain from a numerical dynamo model looking at this issue. This is some runs using magic. Here's our model setup. I don't think that's actually particularly important to this story. So what I've done here is to take the magnetic field output at the top of some insulating region. Obviously, I could have taken it at the bottom of that insulating region equally well. And at that point, at level 1 here, the potential field and the dynamo poloidal field are the same because we're in an insulator. Then start downwardly continuing the potential field, which we've determined at the surface, and compare that with what the poloidal field is from the dynamo model at each of those different radial levels, and see how different they actually are. And if we're trying to get down, you might think sort of some conductivity around here, conductivity is on the left, some conductivity around here is when the magnetic Reynolds number is becoming reasonably large, and we might begin to at least be able to apply some aspects of frozen flux theory. So we're going to make this comparison at each depth as we downwardly continue. So what I'm doing in these plots is to show the potential field spectrum as a function of spherical harmonic degree in red and the poloidal field spectrum in blue. Now, at level 1 and level 2, we're in the insulating region, and obviously the two spectra plot one on top of the other because it's an insulating region. That's just to sort of show that nothing's going crazy wrong here. I should also point out that these spectra are only going out to degree 64 in these plots. The actual model goes out to degree 1000 or so. So I'm just showing a tiny little bit of the spectrum at low degree. And our observations only go out currently to degree 20 or so. So if you're looking at the comparison with observations, it's just the left-hand half of this plot that's really relevant. If you're interested in dynamo theory models, it goes way off to the right. So I've just focused in on this little bit on the left. At level 3, when we're just beginning to pick up some electrical conductivity, you can maybe see that one or two of these symbols for the spectra aren't quite plotting directly one atop the other. So now, having reached the region of electrical conductivity transition, let's see what happens at these next 3 levels as we go deeper into the region of electrical conductivity. At level 4, surprisingly, given we're now at a conductivity of sort of say 5 times 10 to the -3 or something, the spectra are plotting one on top of the other. And the RMS difference in the fields, which I haven't shown here, is still quite small, just a few percent. Then, as we go deeper, you can see that the spectra are now differing. We're up here at level 5. And then at level 6, the spectra become quite different. But I think there's an important message here as to why they're becoming different. It's not because as you get down into the region of electrical conductivity, the field suddenly gets much stronger. The field strength actually isn't increasing much as you get down into that region of electrical conductivity. But if you downwardly continue the surface potential field to smaller and smaller radius, that is blowing up as you go deeper. So it's the potential field that looks much stronger at high degrees, as one would expect, than what the actual field is at that depth. Here we are at level 6 at the top of this stably stratified layer, which is really there just because I stole this output from some other runs that Rakesh had been doing, which had a stably stratified layer in it. But what's happening here is the spectrum of the poloidal field at high degree has gone flat because the field is being effectively stirred by the motions at that depth and producing a largely flat high degree spectrum. Now, as we go into the stably stratified region, it's almost worth just ignoring the potential field at this point, because that just keeps on growing and growing and growing as one downwardly continues. And here we've got, at high degree, 6 orders of magnitude difference between the downwardly continued potential field and the actual dynamo field at that depth. There's no real indication here of the spectrum of the poloidal field going particularly flat. But even here at level 7, if one's just looking at the low degrees, there's still a surprising degree of similarity in the 2 spectra at low degrees. And you'd expect them to be more similar at low degree than at high degree. But the important process here is that once one gets into a region of reasonable electrical conductivity, the field strength in the poloidal field isn't changing very much with depth, but a downwardly continued potential field obviously continues to blow up as you go to smaller and smaller radius. But it would seem we're reasonably safe in getting down to somewhere like the mid-range of the region of electrical conductivity increase, simply because, in a sense, the field is already adapting itself to the potential field condition that it's got to satisfy at the top of that layer. So I would argue that all is not lost at level 5, the midpoint, or slightly above the midpoint of this region. The magnetic Reynolds number is now 100. So frozen flux is probably not a terrible approximation. And yet the spectra and indeed the RMS difference between these two fields is at this point quite small.
Is this a local magnetic Reynolds number or based on the system scale?
That's the local one based on the conductivity at that depth,
Thank you.
as output by your code. Yes. Yeah, so that's using a horizontal length scale rather than a radial length scale. Yeah. So it may be a little less than 100 if you look to the radial length scale. Okay, so in the latter part of this talk, I'd like to talk about some of the new results from Jupiter. The Juno spacecraft pictured here was launched in 2011, arrived at Jupiter in 2016 with a planned mission of 1 year, 32 orbits over the course of 1 year. The sole reason the mission was planned to be 1 year was because that was part of the directive of the request for proposals to have science operations lasting a year. By what is now a very fortunate event with the spacecraft, we had to keep the spacecraft in a much longer orbit than was originally planned. The original orbit was going to be 11.5 days because 32 goes, the number of orbits we wanted goes into 365, 11.5 times. But we were unable to perform the maneuver to go into the 11.5 day orbit. So we stayed in a 53.5 day orbit or 53 day orbit. That's decreased a little recently, which has led to a much longer mission, which is good for detecting changes in Jupiter's magnetic field. And in part because we saved a lot of fuel by not doing the maneuver into an 11.5 day orbit. The operations of the spacecraft are being able to continue for much longer. So instead of having a mission that would have been over by the middle of 2017, we have a mission which hopefully will still be returning data 2 or 3 years from now. So from a year's duration to a 7 or 8 year duration. All thanks to a bad valve in one of the, in the main rocket engine. So the magnetometers for this spacecraft are out here on the end of one of these solar panel arrays, well away, we hope, from fields from other instrumentation on board the spacecraft. Despite being out at Jupiter, the spacecraft is entirely solar powered for its electrical demands. These panels would generate about 14 kilowatts at Earth, and they generate about 500 watts out at Jupiter, which is probably, in practical terms, about as far out as one could go with a solar-powered spacecraft. Solar-powered for the electronics, it's still got rockets on board. So what does the field of Jupiter look like? Well, on the left are 2 models of Jupiter's magnetic field, published about 4 years ago, after 8 orbits of the spacecraft. And the mean time of those 8 orbits is around 2017. And when these maps first appeared, I think the reaction of many people was that, well, these regions are very low flux, really because you've only got 8 orbits. And when we get more orbits, more details, more structure in those regions will come into focus, and we'll see perhaps Jupiter isn't so dissimilar from Earth. But after 32 orbits, a mean time of 2019, 2 more models, again, very little has changed in terms of the distribution of flux on the surface, or at 0.9 RJ on this planet. There's still large regions in which the flux is very weak, and a few regions, the Northern Hemisphere and the Great Blue Spot, where the flux is concentrated. Now, these 2 images have a mean time about 2 years apart. Can we see any changes in the field between these 2 central epochs of the 2 models? Well, it's not immediately obvious that we can. If you look very carefully, you can sort of just about convince yourself that maybe that is a little bit further to the east than it is over here. Maybe the center of the Great Blue Spot also is a little further to the east than it is over here. But the differences are small. However, the scale on these plots is very large. We're looking at up to 4 milliteslas. So, and the accuracy of the instrumentation is somewhere around 100 nanoteslas. So there could be differences which are very significant in the data, which you're simply not going to pick up by trying to visually compare 2 maps 2 years apart. Perhaps the one region where you can see a larger change in the field is at the South Pole. But as I will argue later, that is spurious. It's a function of the spacecraft orbit evolving and has nothing to do with changes in the field in that region. Now, if we look at the actual residuals to the data, we can see some evidence of the field drifting towards the east. What I'm doing here is plotting the residuals after fitting a model to the data. And if the residuals are of one sign, they're off to one side of the track, as they are here. And if they're of the other sign, they're off to the other side of the track. And if we look at the residuals from the earlier orbits through the central set of orbits, this is using 32, to the later orbits, we see a systematic change in the residuals. Here, they're, for this track, going just to the west of the Great Blue Spot. They're of this sign, they're off to one side of the track. Down here, orbit in a similar place, the sign of the residuals has reversed. What's different in the 3? Yeah, no, it's the same background field model in all. Yes, so we've solved for a single field model, not changing with time, for the whole 32 orbit data set, and then looked at the residuals of that field model, the field model that's plotted in the background, to the data along each track. And we see a systematic change in the sign of the residuals with time. And that change is consistent with the blue spot moving somewhat towards the east. And likewise, up here in the Northern Hemisphere flux band, we've also got a systematic change in the sign of the residuals, which is also consistent with that region moving towards the east. So how can we make this a little bit more quantitative? Well, the usual method one would adopt at this point is to say, okay, we'll solve for both the main magnetic field and its secular variations simultaneously, and then invert that combination of main field and secular variation, the time dependence, for the fluid flow, just in the same way that we would analyze observations for the Earth. However, it's not at all clear that we have adequate resolution in time to solve for all 200 odd coefficients that would describe the secular variation. So instead, we're going to take a different approach in which we effectively miss out the step of solving for the secular variation, and we solve simultaneously for the main field and the flow that best produces the changes in the field that are demanded by the data. Now, we are going to make the flow we solve for purely zonal and toroidal. So it's described by a small number of coefficients. It's reducing the number of coefficients that we need to determine by a factor of 20 or 30, Lmax plus 2. Now, by assuming the flow is purely zonal and toroidal, we get around one of those obstacles to applying Robertson-Scott, because we don't have any radial motions because we've assumed that there aren't any radial motions. So that's an assumption we've added, in part because we need to apply Robertson-Scott, but also because zonal flow is just ubiquitous in Jupiter. And there's every reason to believe that there's strong zonal flow in the region in which the secular variation is originating. So this makes the inverse problem nonlinear because the field depends upon the flow and the flow depends upon the field. But we can solve that relatively straightforwardly. And this is what we find. On the left here, this is the blue line curve is the zonal flux velocity that we obtain from the inversion. I'm calling it a flux velocity just because, rather than a flow velocity, because of some of the concerns about using Robertson-Scott, that maybe what we're really observing is the rate at which flux lines move rather than the rate at which the fluid moves, but I think they're probably similar. So we see this blue, or we obtain this blue line, but a large part of the signal we've obtained here can be represented by this solid body rotation in orange. The orange line is the solid body rotation part of the flux velocity that we've obtained. But that's nothing more than saying, oops, we're in the wrong frame of reference. We've got the rotation rate of Jupiter very slightly wrong, so that we appear to be seeing changes in the field, but they're really just because we're looking at the field in a frame of reference that is slightly different from the frame of reference in which the magnetic field is existing. And we can look at both the apparent secular variation, the secular variation that the blue curve would produce up here, and we can look at what I call the true secular variation, the secular variation after one's removed this solid body rotation. And one can see that the true secular variation is much simpler than the apparent secular variation. It's dominated. No, that's what we fit. From the inversion, we obtain this blue curve. And you could argue maybe it's a little underdamped. It should be regularized a little bit more. But yeah, that's the result of the inversion. In both cases, the secular variation is dominated by this eastward motion of the great blue spot. Obviously, if you take a spot and move it one way, you create an area of one sign of secular variation on one flank of the spot, and immediately adjacent to it, secular variation of the opposite sign as it moves, as it translates towards the east. But much of that signal is due to the solid body rotation, this frame of reference problem. And when we look at the true secular variation, we find that's arising almost entirely from motion of the great blue spot due to this jet at the equator in which the rotation rate is greater than this adjustment to the solid body rotation. So a question is this jet that is causing the great blue spot to drift, is it driven from above? Is it due to the projection downward of the strong surface zonal winds, or is it driven from below? Is it part of the flow associated with the dynamo? Kimmy Moore found a reasonable agreement by projecting the surface winds cylindrically downwards, and that was able to not only explain recent changes in Jupiter's field, but much earlier changes in, or much longer period changes in Jupiter's magnetic field, going back to Pioneer and Voyager. Canerney projected the winds instead of cylindrically, radially, so just taking the same profile and using it at depth. And because of this equatorial super rotation, again, you get a reasonable agreement. But in dynamo models, we find that they're characterized by strong prograde jets near the equator. So equally well, this could be driven from below. I guess the bottom line here is that there's a lot of prograde super rotation in Jupiter near the equator, and it's hard to distinguish where it's coming from. I've gone from sort of being in this school of thought to being in that school of thought. And very recently, a paper was published by Shannon et al., in which they did invert directly for the secular variation. There are good similarities between their solution and our apparent secular variation. The secular variation due to the great blue spot, some of this due to the advection to the east of the northern hemisphere flux band. These match up well. But a lot of that is just because of the frame of reference. What they have solved for here is in large part due to being in the wrong frame of reference and isn't true secular variation. They also see very strong secular variation at the South Pole, and that is spurious, and it arises from the evolution of Juno's orbit. Here is what Jupiter's orbit looked like at the beginning of the mission, and it was going reasonably close to South Polar regions. But as the periapsis has precessed northwards by about 1 degree per orbit, now Jupiter is coming down here somewhere, Juno is coming down here somewhere on its orbit and doesn't get within 3 or 4 planetary radii of the South Polar region. So the latter orbits of Juno, of Jupiter, have no resolution in the South Polar region. So it's actually the very last region in which one would expect to be able to detect secular variation. And this is simply the model trying to say, oh, I want a weaker field there because these later data have no resolution of the field there. Slightly more complicated story than that, but that's the essence of it. Okay, well, finally, I want to talk about some very recent passes of Juno, which have targeted the Great Blue Spot region. These 6 orbits have all been in that one particular region because it's where we see most secular variation. And ask, how well does that model I produced from the first 32 orbits fit these more recent orbits that are targeting this one particular region? And we see that systematic residuals have come back in this region. The negative residuals are to the west of the Great Blue Spot, and positive residuals are to the east of the Great Blue Spot. And this pattern is consistent with the drift of the Great Blue Spot actually having slowed down slightly. Those are all BR. It is, if you look at the residuals of the other components, they're much obviously harder to interpret than a residual in BR if you're thinking of flow, because other components of the field are involved in producing the residual in, say, B phi. So we can test whether this is what is indeed happening by producing 2 solutions. One, which is essentially the same as what I already showed you, where we solve for the flux velocity using the first 32 passes. And then in the second solution, I'm going to drop out the early Great Blue Spot passes and only use the later Great Blue Spot passes. We're using all the other passes on other parts of the planet, but here we're using early ones, and here we're using late ones only, and solve again for the differential flow. And we find that the zonal jet speed, after removing the solid body rotation, has reduced by about 15% between these 2 sets of solutions. So this suggests that the zonal jet may be decreasing in speed. It's hard to say anything about timescale with 2 data points, but perhaps on a decadal timescale. So possibly we're seeing some indication of a torsional oscillation affecting the zonal jet speed. Late next year, we have another sequence of passes coming up over the Great Blue Spot. And I think those additional passes will enable us to say much more about what's happening in terms of fluctuations in the rate of drift of the spot. So to wrap up, we've seen evidence of secular variation at Jupiter, but a large part of it is just solid body rotation, requiring a small adjustment in our frame of reference. Real secular variation results in large part from this equatorial jet, and there's possible evidence of time-dependent flow, which might possibly be a torsional oscillation. Thank you.
Thank you, Jeremy. Do we have questions? Yep. Sorry, I'm just.
Is it possible to say something about the presence of turbulence inside the planetary core? For example, question is convective flows and flows in stably stratified regions. They're turbulent or laminar. If they are turbulent, it's the second question, what is the role of turbulence in the generation of planetary magnetic fields?
Well, our observations are restricted in resolution. We've only had 40-odd orbits so far, so the spacing of those orbits is only a little less than 10 degrees. So the length scales we can resolve, at least between meridians, is still very large indeed. So I don't think observationally we can say anything about small-scale turbulent-like motions. Our resolution, though, a long track, the spacecraft is in a north to south orbit is actually much better. And my belief is that we're underfitting the gradients in the field in a north-south direction. We might then be able to say a little bit more. I think Ben had his hand up first at the back.
Yeah, concerning the last point you made, it seems a bit ambitious to not only try to infer secular variation, but secular acceleration. My question would be whether the data quality actually is good enough to allow that, or
Yeah, I was hoping somebody would ask that question. So the drift of the Great Blue Spot produces about 15,000 nanoteslas a year of secular variation. So to put that in perspective, in 2 years, it produces as much secular variation as the strength of the Earth's magnetic field. If roughly half of that, or a bit less than half of that, is true secular variation, that's 6,000 nanoteslas a year of true secular variation. And then if the speed has dropped by 15%, that's around 900 nanoteslas a year change. Over 2 years, 1,800 nanoteslas. We believe the accuracy of the data to be of order 100 nanoteslas. So we're an order of magnitude safe here in making this inference.
Yeah. I was just want to compare what you were just telling us about the secular variation over a few years, if I understood correctly. This is just over the Juno mission that you were measuring this. And I'm wondering how the pattern and velocity compares to what Kimmy was inferring over 4.5 decades.
So what Kimmy Moore, a former student, did was to do the experiment of flying much earlier missions like Voyager and Pioneer and Ulysses through today's Juno determined magnetic field and look at the difference between what those earlier missions actually observed and what they observe today. And she found she could get a good agreement with those earlier missions. Her velocities are higher than the ones obtained here, but right at the equator where the Great Blue Spot lies, they're not actually that dissimilar. So it's within a reasonable factor.
Well, I was just going to ask a question about that, actually, because I mean, in your flux velocities, there was less than a centimeter a second, wasn't it, in that picture you actually showed? So that is considerably less, isn't it, than the few 2 or 3 centimeters a second, or even 4 centimeters a second, I think Kanani was mentioning at one stage. So, I mean, this is nearly a factor 10 different, isn't it? So where are we exactly on this?
But the peak velocity in Kimmy's work was actually up here rather than down here, where it's got nothing to advect.
Yeah.
It's the velocity around the Great Blue Spot where you've actually got something for the velocity to work on, which is what we're sensitive to, where obviously we have very little sensitivity to the velocity where there's no field to be advected, or no gradient in the field to be advected.
Right. So you think actually the smaller ones are more likely to be
That's
right. So
well, that's my bias. Yeah,
that's your bias is less than a centimeter a second. Yeah. Okay.
And I think an argument for, or an argument against these flows being a manifestation of the surface winds projected downwards is the surface winds are of order 100 meters per second. And if they're projected downwards baroclinically, then they've got to reduce to roughly 1 centimeter per second by 4 orders of magnitude without the pattern changing much.
Yeah.
And I find, in retrospect, that a little implausible. Yeah. And so I tend to favor the idea that it's a
No.
dynamo jet that's
Yeah.
causing this
Yeah,
secular
because I mean,
variation.
for a long time, they've all been producing these equatorial acceleration
Yes.
jets, haven't they, in a fairly consistent way. Just one other quick point about this work on the sort of variation of the speed. Is this actually published yet, or is this still in preparation? I mean, the very last thing you mentioned at the end.
No,
No.
that's in the last several weeks. So that
Right.
hasn't
Yeah.
yet been-
I mean, as you know, there's been quite a lot of work on possible torsional oscillations in Jupiter. And I
Yes.
just wondered about that. Yeah.
Okay, we've got time for one more question.
Historically, there was this dichotomy that we now realize may be false between the notion of the zonal flows being driven meteorologically, that is to say, in the atmosphere where you can get fairly large entropy gradients, versus a surface expression of deep-seated convection, an idea often attributed to Busa. I'm struck by the fact that even though the Juno data suggests that this may be a false dichotomy, we're still in a situation where we don't really have a dynamical theory. Now, I'm well aware, of course, that people run numerical models, you know, Rakesh, Moritz, other people, Uli has done stuff where people think that they can understand the zonal flow. But I would offer the following suggestion or thought and be interested in your reaction, that this is an unsolved problem, that we don't actually know how to construct the zonal flow. And yet that's key to understanding this and other aspects of the problem. The Juno data show, including in the most recent work, which Yochai Caspi has done with Ryan Park, that there's a very strong connection between what we see in the atmosphere, in particular the 20 degrees north prograde jet, and what we see in the gravity field. And the gravity field we know must be deep-seated because it has to come from density anomalies that are large compared to those that could be of relevance to the atmosphere. And if you want to understand the truncation of the flow with depth, if you want to understand this issue that you dealt with early in your talk about what the so-called local Rayleigh number is, which here I'm thinking of as zonal flow as the velocity scale and local electrical conductivity. We don't even know if that's a monotonic function. That is to say, the flow in the atmosphere is 4 orders of magnitude larger than the flow of relevance to understanding this. We don't really know what's happening in between, and we don't have a dynamical theory for it. We don't understand why Saturn's winds are stronger than Jupiter, Uranus and Neptune stronger still. I'm suggesting that we have a major problem in front of us. It could be that exoplanets will help us understand this, but those are some thoughts I have. I'd be interested in your reaction.
Well, I agree. I think we have a major problem trying to understand these zonal winds. I would say it's actually a good problem to have, that we have observations that we don't fully understand, yet we've got constraints from multiple other instruments, whether it's gravity or magnetic field, on those observations. And I think the challenge now is to explain this in a self-consistent way, rather than sort of just the output of a dynamo code. I completely agree. It's a challenge that we have. One thing that Dave was alluding to is the agreement between the gravity inferred from the zonal winds and the gravity as determined from Juno observations now extends to quite high degree, to degree 30 or so. But that doesn't mean that there are sort of degree 30 length scale winds. It's actually the sharpness in the transition from east flow to west flow between the belts and the bands or whatever it is. I never remember which way around they are. It's the sharpness of the transition between the regions of oppositely signed zonal wind that is giving the high degree structure. It's not that they're small scale winds, it's just like a step function and taking the transform of that step function.
Okay, thank you. Apologies to those who didn't get a time to ask their question. I guess there's more. We'll have more time in the discussion this afternoon. So next we have Aokawa, who's going to